To get this started, and this goes to you, Chip, what repeating patterns have you seen from the early days of Silicon Valley moving to today?
Well, thank you, James. And thank you for the fashion help. So one thing James didn't mention is I had a minor in history. And while I don't believe that history repeats itself, I do believe it rhymes. And I think a lot of what we'll be talking about today are those rhymes in Silicon Valley. And if you're interested in the history of Silicon Valley and the semiconductor industry, I really want to recommend a phenomenal book that came out just a couple of years ago, maybe a year ago, which is Chip Wars by Chris Miller. Great story. So to get to the heart of your question, James, really Silicon Valley began in the mid-50s at Shockley Labs. And what Shockley did, who was a Nobel Prize-winning physicist, co-inventor of the transistor, was bring together some of the best and brightest minds to develop more transistor-based technologies. But he was such a horrible manager, 8 of his employees, his smartest employees, actually left. And they formed a company called Fairchild, and Fairchild went on to invent the integrated circuit. And then Silicon Valley really traces its origin from those smart folks that then left Fairchild and created Intel, AMD, LSI, National Semiconductor, and a host of other companies. So what did those folks have in common? Well, all of those smart folks that left were obsessive about bringing together the brightest people to solve some of the greatest technological challenges of their times. These most capable folks were able to achieve great things in their existing company, and recognizing their worth and their confidence, were able to go out and start new companies. And one of the cool things that was invented at Fairchild was employee stock ownership, so that individual employees had a vested stake in the success of the company. And that was all supported by a new funding model called venture capital that had its risk-taking origins here in Silicon Valley as well. So you take smart people, give them a motivation, a financial motivation, give them ownership in their companies, and they'll do great things.
Okay, with that, I'm going to bounce this to Bruce. And just to kind of level set everybody real quickly, you know that none of the stuff that you guys are doing today with technology would exist without semiconductors, right? It became uncool after about 1995, and now it's cool again. And with that, Bruce, AI's got a long history of trial and error. Kind of step us through that history in Silicon Valley, key milestones, and what do you think has brought us to this point today with AI?
Well, let me see if I can summarize about 3 weeks of discussion into 2 or 3 minutes. I think the lessons to be learned from watching AI over the years is how timing is everything. Because as many of you probably know, like general purpose computing and the roots of AI were all started as far back as Chip already referred to this, back in the 50s. First mainframe computer was in actually the 40s. And the understanding of neural networks as a biological phenomenon in biology came originally in the 40s, from what I understand. And then by the 50s, scientists and engineers were thinking, how do we repeat the concept of neurons and neural networks in hardware and software, unlike what's in the biological systems? And that got great enthusiasm going. And of course, there are many other AI technologies other than neural networks, but I'm referring to neural networks because it's kind of a repeating pattern all the way from then to now. And over those coming decades, a lot of excitement. It showed great promise, but it never was good enough, and in fact got shunned, and nobody wanted to hear about it anymore. And then there were a couple of sequences of AI winters, never a huge breakthrough until, frankly, what we've all experienced in the last at least 15 years. You know, and fundamentally, the big change that it was like a tortoise and the hare, by the way. You know, there was always this general purpose computing could handle so many things and all kinds of applications. AI was very specialized, but it was only when you had the huge firepower of cloud computing, highly interconnected compute power, huge storage. Then, like 10 to 15 years ago, I just saw an interview recently with Jan LeCun, that leads AI at Meta, talked about how when they started the research behind what's now considered deep learning, they didn't want to call it neural networks because everybody was tired of that term. They didn't want to use that term, so they called it deep learning. But now there's no shame in the term neural networks anymore. Anyway, I mean that brings us to today, and it's not like one of these general purpose computing versus AI is like a winner or a loser, but clearly the big problems that, like imagine a large language model hand coded in traditional computing. You'd have thousands of programmers working forever, and they would never achieve what a large language model can achieve.
Well, I think we might have some controversy here in terms of view, which is good. I like controversy in a panel discussion. Where is Bruce misinformed, Chip?
Well, let's step back for a moment. How did we get here? I'll give you I think you gave a software view of how we got here. I was a hardware guy. Let me give you a hardware view. Intel recognized back in the early 70s that there was a concept called microprocessors. And they could take, because of the power of the transistors, Gordon Moore had predicted what became Moore's law, that transistors would double every 2 years. So given that computation availability, Intel had an opportunity when they got a contract to make some calculator chips to make a microprocessor, and that became the 4004. And they could see that this microprocessor idea could essentially double its power as the transistors doubled on the chip. So the 4004 begot the 8008, begot the 8080, the 8086, the 8286, 386, etc. But Intel had a problem, and the problem was they started making the hardware faster than applications could use it up. So they came up with the idea of let's make it easy for people to adopt that hardware. So they started creating software development kits and tools to allow smart people to create applications to sell more chips. Essentially, Intel is a greedy company. We sell more chips, we all make more money. Go back to employee stock ownership. So now let's fast forward to the early 2000s. Can anybody think of another company that had a powerful chip, but it was in a niche application? Anybody in the audience? NVIDIA, thank you. Spark's another good one. Right, Sun, that's another good one, a good example. So what does NVIDIA do? In 2006, they released something called CUDA, which is a software development platform to allow smart people to get access to the little bits on their graphics chips that there's lots of. What are there lots of? The ability to do math, matrix math, because 3D graphics is based on a large amount on doing lots of math, and because it's graphics, it can be parallelized. So they gave away CUDA, and just a few years later, a lot of smart people were able to take the algorithms that couldn't work on traditional computation machines and port those applications into highly parallelizable machines that were available in graphics processors. So in a few short years, you had solutions for natural language processing, image recognition, autonomous control systems. So, respectfully
but Bruce, I mean, one of the things I remember when we were at Intel, I remember we had one strategic long-range planning session, and we were trying to decide, and this is when we were at Intel together, should Intel prioritize the gaming market, the high-end gamers, right? People with real fast graphics cards from NVIDIA, no less. And I remember we deciding not to do that. Was that a bit, or not to make it a high priority? At least that's as I remember it. So how did NVIDIA kick our former employer's butt?
That's wonderful.
That's a tough one. We won't tell Pat your comment. Promise.
Well, I recall debates around the gaming because I left in '97, and at that point it was pretty clear that the gamers really demanded the peak performance, and we could always eke much more margin points out of people who bought for gaming than your typical average business computer or not, whatever. But to the point of NVIDIA, None of us can speak for them because we weren't there, but my understanding is from the ground zero when they designed the GPU, it was purpose built for 3D graphics. But on the other hand, they were very clear in making it as Chip referred, a CUDA software layer that would enable generalized high performance matrix math calculations. And they were, I don't mean to in any way take away from them, but they were at the right place at the right time. When this boom hit, they had the perfect product. And many of us see semiconductor companies arising to try to take them on. And many semiconductor companies are trying to build machine learning purpose-built compute engines. And many can build arguments that they have a better solution, but boy, it's very hard to unseat the incumbent. And these software layers are so thick that it's hard to break through. So, but big opportunity there.
Well, then let me ask a follow-up question, because there's certainly AI has some unique workload requirements. Why don't you help the audience understand kind of your view of those workloads, and why is NVIDIA so well positioned to be able to take advantage of that?
Well, in part, Chip's probably better capable of answering, and he already did to some degree. Like the fundamental bottom line in machine learning, and therefore eventually Gen AI, it's all about rapid matrix multiplications and accumulations. And so they can build very simple cores, way smaller than an Intel core, but the latest, the H100 GPU, well, I guess they've announced the H200, I believe, from NVIDIA. So these things have thousands of cores. Yeah. I mean, that's kind of, in our day, that would be a mind-boggling concept.
Mind-boggling number, yeah. Yeah, so again, one of the big things, again, we want you to walk away with is when we were at Intel, and I remember when Netscape went public in August of 1995, soon thereafter somebody came up with a comment that software is eating the world. And then everyone assumed that advanced silicon was just gonna be there. You can't assume that anymore. So there are some unique challenges, not just in the design piece of this, but also in the manufacturing of these processors. They are the single most complicated machines on the planet. And Chip, why don't you comment, because you've designed some of these hairy things.
Well, I have, and thank you. I mean, so this is a really interesting question. Is Moore's Law going to end? Because if Moore's Law ends, then we won't continue to see these rapid improvements. So in the strictest sense, will transistors keep doubling every 2 years? Well, it's already slowing down as we get to the physical limits in the atomic scale of making transistors. But there's a lot of technologies that are starting to be deployed now that if you take a bigger picture of Moore's Law, it's not ending. So if you move off of a single chip and can start doing multi-chips, which Intel and others are doing today, that's one way around it. You have quantum computing, you have photonic computing. So personally, I believe that smart engineers will be able to keep pushing forward on doubling computational performance. Maybe not purely with transistors or monolithic transistors, but in more complicated solutions.
Hey, Bruce, some of your thoughts around here, this area?
I yield to Chip.
You yield to Chip. Okay, you're not gonna try to compete with the designer of the 386. Okay, that's fine. But you may or may not have heard that you've had Sam Altman. All you guys know who Sam Altman is, ChatGPT. He's been going around the world saying that we collectively need to invest $7 trillion. Big number to handle the future workloads. And that's why I keep wanting you to comment on workloads, because that's what's going to drive demand for advanced silicon, and whether we're going to be able to build all this stuff. And are you going to do it all in data centers, cloud centers? Are you going to push it to the edge? What are you going to do?
Well,
Both.
go ahead.
Both.
Yeah, both, I know, but right now Azure, AWS, those are all big cloud environments. You know, we're not leveraging the edge.
No, James, I think, first of all, I think there's multiple things here. There's training the models and using the models. Training the models typically gets done in the data center because you need to bring together all the data and crunch it and run it. but I think we're seeing more of the execution getting pushed to the edge and adoption getting pushed to the edge. And as, just take Apple, they put more AI computation in their phones. You see more announcements, the Copilot PC. All these things are seeing AI processing getting pushed further out, and then I think models can be adapted, learn, and then be fed backward as well.
Bruce?
Well, I was just going to say, the underlying technology that Chip's describing is a little out of my area, but my suspicion is, I don't know to the extent there are many chip startup companies around in this event, but I think the opportunities for chips are probably more on the edge than in the data center. Because for example, power consumption is extremely important. If it's a mobile technology or in a car or whatever, it's got to be super low power. I do think that's the bigger opportunity. I would like to answer a related question that you haven't asked me
please.
yet, James.
Please ask my question.
Like when you talk about this $7 trillion demand, you could debate, is it 2, 4, or 7? I don't know, but I'm betting on, I'm hoping for success with the likes of Intel, because we really want to have manufacturing of this kind of technology here in America. So, their $20 billion fab in Ohio that's going to be followed hopefully with like $100 billion of investment. It would be great if that works. I don't own their stock anymore, but I would love to see them be successful.
I still own way too much, and I want them to do something to get my stock price back up. But no, this is serious stuff. What Bruce and Chip have commented on is to build a modern fab right now is not only mind-boggling complicated, but a $20 to $25 billion proposition for one fab that may produce their first chip maybe after 3 years, or is it 5 years? Yeah, it takes, you make big bets on what you're going to build 3 years before you build it.
One thing, I'm sorry, just real quick. Like, when I arrived at Intel in 1980, I worked in a development fab. Process development was happening there. That fab was probably the size of this room. And then you see these pictures of their modern fabs. These things are well bigger than a football field, and then there's just rows of those. I mean, the scale of these things are just mind-boggling. I'm in awe.
Chris Miller in his book points out a modern fab costs as much as an aircraft carrier, and it's obsolete in 5 years.
Yeah, and by the way, a fab costs you the same amount whether you build one chip or millions of chips, and you have to make those bets way up front. Right, so this is in order for AI to happen the way that all of the pundits that you listen to and you watch YouTube videos, it is predicated on somebody building those fabs, right? And when I left Intel, I think the fab cost was only $3 billion. Now, these are step function, the most complicated machines to build the most complicated machines that humanity has ever built. One more comment, Chip, and then we'll ask for some questions here.
So the only comment I want to make is I think it's very easy for all of us to get caught up in the technology, but what concerns me, and the question you didn't ask, is what's the other side of this? And I would charge everyone in this room, if you're interested in AI, you need to be thinking about the ethics in AI. And just to recommend another book, Your Face Belongs to Us is a really powerful story written by a New York Times reporter, Kashmir Hill, about Clearview AI and building facial recognition systems without anyone's permission to do it. And while I think it's easy for us technologists to get really excited about this stuff, we as a society need to really think about and demand there be protections around AI.
I agree. Bruce, any final comments before we take audience questions? Okay. Folks, please, someone's got to ask a question. Otherwise, we're just going to sit up here and start arguing with each other because we're ex-Intel guys. That's what we do. No questions? There we go.
Stand up, please. Speak slowly and say your name first.
Yeah, hi, my name is Ronaldo Gilt. My question is, where does this end as far as energy per square foot? Because this thing is really it's on the same trajectory as the Pentium was, and then Intel had to move into multi-core. So what are we going to do to stop that energy curve?
Chip, that's probably, man, but we've been gone so long. It's hard to tell.
Well, I think you're asking kind of two questions embedded. Again, there's the edge and the data center. So I don't know the specifics. I've not looked at, say, NVIDIA's microarchitecture that closely. Certainly, all the semiconductor companies had made huge strides to do better power management on chip, and moving to more advanced process technology also help. So I think it's certainly not like Intel in the 90s, where power never came up, and was in part why Intel struggled for a while in mobile, initially in notebooks and then in mobile computers, where Intel basically said, we're not going to play in the portable mobile space, these devices. So I would think lots of work is going into that, but I'm afraid I don't know specifics.
Any other questions, guys?
Next up, say your name and speak slow.
Hi, my name is Maxwell. I'm an undergrad at UC Berkeley. And my question is, can you describe the supply chains for semiconductor chips and perhaps elaborate on some of the geopolitical risks to those supply chains?
So supply chains
And geopolitical risks to the supply chains.
We talk about this a lot, actually. Bruce, why don't you start? Let's go. Bruce, Chip, and me, and then we'll probably need to wrap up then. Go ahead.
All I can say is, first of all, Maxwell, I hope you're majoring in double E, because that'd be a perfect name. But all I can say is the obvious. It's just not good that we depend on these. In our day, we were busy moving things around the world for the economics of it, but now the world really has changed in the recent decade or two. And having the vast, I don't know if it's the majority, but a significant portion of the worldwide semiconductors produced in Taiwan, with the unfortunate risk there, it's just not good. So kudos for the CHIPS Act, in my humble opinion.
So I think there's a couple of things. There's the location of fabrication plants themselves, and there's the equipment that goes into them. One of the most important pieces in a modern fab is lithography, which basically there's one company in the world, a Dutch company, ATMSL, who makes e-beam lithography equipment. So there's a choke point there. So you're seeing, I think there's a lot of national security implications to your question. The CHIPS Act was in part inspired for national security concerns to make more capacity available domestically. You're seeing the same thing in Europe. So I think the supply chain is changing because of those national security interests. But today, it is most of the world's for sure, most of the world's chips come out of Asia, mostly out of Taiwan.
Yeah, Maxwell, that is an excellent question. In fact, this is a topic that the Intel Alumni Network is going to debate in earnest at a big event in Q4 that we're going to do about the future of manufacturing, from design tools for semiconductor design, which is what NVIDIA does, by the way. I hope all you guys know, NVIDIA doesn't build any chips, right? TSMC does, Samsung and Intel, right? And we're going to talk about from design tools through finished goods inventory, because to Chip and to Bruce's point, if we just move the choke point in the supply chain, right, from semiconductors to PCBs and cables, that's in effect all you've done. And the last comment I make, I promise, Rob, we'll get off the stage, is I was at a dinner with the former head of Intel Foundry Services and the author Neil Ferguson, who many of you may know. And what he told me is that he got a phone call a week from a head of state pleading with him to build a fab in their country, right? So this is, we've gone from when the three of us left Intel, semiconductors weren't cool, they're cool again.